Good afternoon, everyone. This week we are going to talk the soil sampling strategies and basic analysis of the soil samples. The lecture objectives for this week is why is soil sampling needed, and what are the soil properties we consider when doing soil sampling, and what soil sampling methods are used, and some factors to think when design soil sampling. And in the end, we will introduce some on-the-go soil sensing techniques. Why is soil sampling needed? It is all because of the variability of the soil, and we know that in some part you find relatively uniform soil, and for this kind of field, it has low potential benefit from precision ag. However, in some part you can find extremely varied soils which can benefit greater from precision ag. And by doing soil sampling, you can find these extreme variations, and also it is an inventory of the available nutrient supply in the soil. It considers soil type as one one character of soil, and also as other fundamental soil characteristics like soil fertility or soil structure and soil pH, etc. And we know that conventional wisdom is that the growers will always over fertilize their field as insurance so that they get the highest yield. However, in places that the soil nutrient is high enough that it doesn't require any fertilizer, you are still applying the same amount. So that is a waste of fertilizer and also a waste of input. Eventually, it lowers the farmer's benefit or profit. It lowers the farmer's profit. The essential soil properties for understanding variability and for understanding spatial variability in the field includes soil fertility, soil pH, soil organic matter content, soil water supply, soil structure, soil type, etc. So for soil fertility, which is very important when growing agricultural products, the primary nutrient the crops need nitrogen, potassium, and phosphorus, NPK. And also the crops need secondary nutrients such as calcium, magnesium, sulfur. And there are more micronutrients that the crop requires, and usually people might find, for example, iron deficiency in the field, which cause some symptom in, for example, corn. Maybe I can show some example pictures of nutrient deficiency in field by crop symptoms. So what are some of the soil sampling methods used in precision ag? This is a chance for you to discuss in group and come up with some soil sampling methods, and we can discuss more a little bit later. In the past, when people do soil sampling, most of the time they take the average of the whole field and make fertilizer recommendations and applications in one uniform rate. But in precision ag, we want to know more about the spatial variability in soil in the field. So we come up with different soil sampling methods that meet the grower's requirements and best describe the spatial variability in the field. Some methods are simple random sampling, stratified random sampling, and grid sampling. So the simple random sampling is just like this. You have a field of this size and you decide, okay, I'm going to collect 20 samples from the field randomly. So you randomly pick 20 locations and collect the soil sample at those locations and this is called the random sampling. If you have some prior knowledge of the field, for example, you know the soil type difference from place to place, like what is shown in this picture, then you can use soil type sampling, which is one method of stratified random sampling. So in each soil type, you collect multiple samples randomly or by some kind of scheme and target every single soil type with those samples and analyzing them independently. And in the end, you will get different recommendations for different soil types based on your soil sampling result. Soil type sampling is to sample sections of the field that have similar soil types. Usually you can get this kind of information from soil survey maps by USDA and NRCS, which is Natural Resources Conservation Service. These can be the reference for you to select the sampling locations. Also, you can design a soil type sampling based on Web Soil Survey, WSS. You can find it from this link. And soil type sampling results in samples being taken from different spacing around the field, like what is shown in the previous picture. So other stratified random sampling include can be based on yield data or some other management data from previous years. And here's an example of based on yield data. By the previous year's yield, you can separate your field into several major sections in each of the sections you have an approximate yield level measured. So in the end, you separate the fields into these yield levels and design a sampling within each of the yield levels area. So next is grid sampling. Grid sampling divides the field into square sections and gather the soil samples in each section. Grid sampling is used for better estimation of soil nutrient status on a smaller scale than the entire field. So grid sampling, and there are two methods for grid sampling: grid center method and grid cell method. So this is the grid center method, where you collect the samples in the center of each grid, or maybe in the crossings of the grids that you get. Anyways, you are getting your samples from evenly distributed spaces in your field. And for grid center sampling, the common grid size is about 2.5 acre, which spans about 330 feet long and wide. Sometimes you can collect samples every 1 acre or 4 acres, and the sample depth depends on what you are sampling, and also depends on the soil type and soil structure and everything. And the normal recommendation for phosphorus and potassium is 0 to 8 inches from the surface of the field. And for lime application, you sample from 0 to 4 inches from the surface of the field. So for grid cell sampling, several samples are obtained from each cell, but since you treat the whole grid, you treat every single grid as uniformly distributed soil properties, the entire grid cell is treated. You take an average of all the samples collected from a single grid cell as the soil property of that grid cell. This is an example picture of grid cell sampling where you collect 3 samples from every grid cell and then take average of the cell. After the sampling, the samples will be sent to a soil testing lab. Usually the testing takes several days or weeks, and as technologies are developing very fast these days, there are some on-the-go soil sampling units that you can buy from the market. And the results, soil sample test results are used to generate soil properties map by interpolation, which we will talk later, next week or next week. And 1 layer per property. For every single property, you get 1 layer in ArcGIS, as what I said before. Layers. Remember layers from ArcGIS? You have the states, you have the United States state map, state boundary map, and you have the USA county map, you have USA farm density map. And every single of these are a layer that you can put and show and calculate in ArcGIS. So next, we are going to talk about selecting and designing a sampling program. Questions to be answered before you have a final design of the soil sampling program are: how often should I sample? When should I collect samples? What factors affect the outcome of my samples? And how to decide appropriate number of samples? How often to sample? Factors to be considered are soil type, previous soil nutrient levels, cation exchange capacity. This is to measure the soil electrical conductivity, and it's an indicator for multiple soil properties such as your soil structure and soil type, and also water table depth, and also crop systems such as irrigation and crop rotation. Current recommendation is every 2 to 4 years for soil pH, soil potassium, and soil phosphorus. And there's no single recommendation that exists. So it all depends on the different factors that you need to consider. And the soil sample frequency can be as high as per season or per year. When to collect samples. Farmers should sample close to the same date each year so that to minimize year-to-year variability. So you don't want to collect samples this spring and next fall, because spring is here is the beginning of the crop cycle, but fall is the end of the crop cycle. You can expect more soil organic matters in the end of the crop cycle, because you have the biomass that is the biomass from this year's crop left in the field to increase the soil organic matter. Farmers should sample in spring or fall, and so as to avoid rapid change over midsummer. I think this is quite understandable because during midsummer, the crops are growing very fast, changing status from week to week, and also there are rain and also a lot of farm management happening during midsummer. So if you take samples during the summer, you will get very large variation from one large variation. For example, comparing before fertilizing and after fertilizing. And farmers should seek the best recommendations for each single local conditions. Factors that affect soil analysis results include sampling near the field boundaries, because the soil may vary due to external factors. You might have machines traveling around the field boundaries, on the field boundaries, and also so it causes different soil structure compared to your crop planting area. And sampling near gravel roads can cause the variation of limestone in the gravel and also the soil pH level, because we know that limestone has higher pH level. And sampling near the fertilizer beds should also be avoided, because the samples from fertilizer beds in row crops will have higher nutrient levels than the surrounding areas where you don't have direct fertilizer mixed into the soil. How to decide the number of samples? Suppose you have some prior knowledge of the field, say previous year's soil sampling data. So we are going to introduce several descriptive statistics for soil sampling. Measures of central tendency include mean and median. So it tells us an overall idea about the average level of the field, but it doesn't tell us if the field condition varies a lot or it is relatively uniform. So we need measures of spread, which include variance, standard deviation, and coefficient of variation. And frequency distributions also show information about both measures of central tendency and measures of spread. Mean is average. So for example, if you have a bunch of soil samples value, and it's easy to get the average of the soil sample value, right? And median is the middle value of all the samples. I'll give an example to show the difference of mean and median. So you have soil pH value for 10 samples: 6.7, 6.9, 7.1, 6.5, 6.9, 6.6, 6.7, 6.9, and 7. So mean is just simply the average of the soil pH values, which give you 6.83. Is it easy enough to understand? I think so. So when you try to find the median, you sort the samples in order from smallest to biggest. So you get 6.5, 6.6, 6.7, all the way to 7.1. And the median is the average of the 5th and the 6th, which give you 6.9. So it's different from the mean. It's the middle value of the whole soil samples. Here are the definition of variance, standard deviation, and coefficient of variation. You might see this familiar because we mentioned this before. But the variance, and the coefficient of variation is standard deviation divided by the mean. So again, we use the same soil pH example. How to calculate the variance? You have n equals 10. You have 10 samples. Xi is every single value of the soil pH, and X bar is the mean of the soil pH. So following this definition, you put all the values in, and in the end you get 0.038 as your variance. And standard deviation is simply the square root of variance, which give you 0.195. Coefficient of variation, again, use the equation that I gave you. Input as standard deviation, which is 0.195, and input X bar, which is the mean, 6.83. In the end, you get 2.8%. So up to now, you can decide the number of samples. Number of samples have a rule of thumb equation that you can use if you don't have any other information for deciding the number of samples, which is 1.96 times standard deviation divide by the tolerance value and square the total, and you get the number of samples. N is the number of samples, sigma is the sample standard deviation, which is S, or square root of S squared. D is the tolerance value, the maximum allowable difference between the measured mean and the predicted mean. It can be 0.2 or 1 or 2, etc. That depends on how tolerable you are about the variance. So, for some soil properties like pH, bulk density, crop yield, soil water infiltration rate, soil nitrate, which is the nitrogen content, and soil phosphorus, you can see that they have different magnitude of variability, which is a guideline for you to carry out soil sampling. If you have magnitude of low magnitude of variability, that usually means that you don't need to collect that many soil samples. But if you have very high magnitude of variability, that means your field varies a lot on that specific soil property, such as soil phosphorus. In that way, you want to collect more samples to precisely estimate the variation of the field, so that to guide you for further applications, such as phosphorus fertilizing. So after these calculations, we want to discuss what these calculations tell us. The mean, the variance, etc. So here is a general view of what happens if you map these. What happens if you map the values, the measured values? If you map the frequency of the measured values here. So, with low spatial variation, such as soil pH, you might get a histogram like this. Oh, I think I will draw this on the board about histogram, about what sigma tells you, what mean tells you. So next I will see if I have time to continue about some examples, some example calculations of mean variance and coefficient of variation in Excel. Okay, this is the end of this lecture.